Not typically. All right. Hello, everyone. I think we're going to get started. My name is Jenny Callahan. I'm a postdoc here, and I'm happy to introduce Colette Salyk as our colloquium speaker today. Colette is a professor, associate professor at Vassar, and the Mariah Mitchell Chair in her department. She's also one of the leaders of this collaboration JDISCS, which is a really cool consortium of protoplanetary disk observers with JWST that have come together to combine data and combine power and knowledge, and I'm really excited for her to share the results. So without further ado, go for it.
Now, can you hear me? Yeah, I can hear myself. Okay, good. All right. Well, thank you for having me here. It's a pleasure to be back in Cambridge, where I went to college. I went to a different school, which you may not have heard of, so down the river from here. All right, so I'm going to tell you about planet formation today. Before I start, I just wanted to tell you where I'm from, because I'm from Vassar. Not everybody is familiar with it, and it's just a really cool place to be an astronomer and also a woman astronomer. So the very first faculty member at Vassar was actually an astronomer, Mariah Mitchell, who was a famous astronomer at that time. So you can see there, that's what we call our Mariah Mitchell Observatory on campus. No longer used for actual astronomy, because it's got like a dome made of bricks, and also right in the middle of campus. But you can see just how cool it is to see these old photos of women doing astronomy, in the, I guess, late 1800s. We have other, and here she is down at the bottom there too. All her pictures, I think it's the old style to look very stern in pictures, but she also was very funny. Like, she wrote these funny poems for her students every semester. Vera Rubin was also an undergraduate at Vassar, and this is a picture of her actually looking through one of our telescopes. And Debbie Elmagreen was one of our faculty members for many decades and a Harvard alum. And there's me trying to walk in their footsteps. And of course, here in the audience, we have Clara Ross, who is a grad student here at Harvard. So just very, very cool women astronomy at Vassar. Okay, so what I want to do today is start by just reminding you of kind of a canonical planet formation story and tell you about some of the wrinkles, what it's missing. And then I'll tell you about MIRI-MRS, the instrument on JWST that I've been using for studying planet formation. And then I'll highlight some of the recent results from my team, which is known as JDISCS. So let me just start with the basics of planet formation. I know you're all experts, and you probably teach these in your classes, but let's just review. So I think if you get down to the very basics of the planet formation story, the solar nebula story, it essentially just says that if you combine volatility of different materials with a temperature gradient, which is set up by the star, then you end up with a compositional gradient. And so the story goes that, for example, let's say you're considering Mercury's location in the solar system, only the materials with the highest sublimation temperature are available to form that solid body. And as you step out, you start to get more, relatively speaking, volatile species. So maybe you have more silicates when you get to Earth. When you get to Jupiter, maybe you have water in the solid phase. And it can actually be incorporated into the solid body that Jupiter's going to form out of. And so on, and you can keep stepping out. This also has an important implication. So water is a very abundant species in the early solar system. And so when the water freezes out, you actually get a pretty big increase in mass. It may do some other things as well. It may increase pebble mass, which is may also speed up planet formation. It may make things stickier, which also can speed up planet formation. So lots of reasons why water may speed up planet formation and allow gas giants to form. And then this also informs the not just the solid body, but also the atmosphere that surrounds the planet. So this is work from Karin Oberg. Just a very simple model saying, hey, if you freeze out some material, then whatever's left becomes your planetary atmosphere. And this is really important for exoplanet studies because ultimately, we're not probing the cores of exoplanets, we're probing their atmospheres. And so this gives us some predictions of what we expect atmospheric compositions to be. And it's also neat because if things move around, you can maybe try to trace them back to where they formed by looking at their atmospheric composition. So that's the basic story, but we've known for a long time that this paradigm is not the whole story. And a lot of that really comes from the solar system. So we do have evidence in the solar system of inherited materials, things that seem to have come directly from the ISM. Models also kind of suggest that there should be materials that are minimally processed in the star formation process. We also know that things vertically and radially mix. Radial mixing is something we can see in our meteorite signatures and so on. And so if you want to have a real complete picture, you need to have inherited materials, you need to move things around. And then the other important thing is that, let's say you move things around, but you allow everything to come to equilibrium, it kind of resets itself. So it's also the case that there's a lot of non-equilibrium chemistry, and everything kind of has a different equilibrium timescale. So things can get pretty complex. This is also ignoring planetary migration, which I'm not going to touch on at all in this talk. So of course, even after the planets form, they can move around, and that's going to change what you find where. And so I just want to bring up, again, in a little more detail, talking about mixing. So mixing is, you have to be careful about what you mean when you say mixing changes things, because actually in the solar nebula story, kind of one of the inputs to that story is that things get fully mixed. But they are allowed to come to equilibrium. So if you fully mix everything around and then you let it come to equilibrium, that's actually the solar nebula story. And so the more complex story actually needs to have things kind of differentially move around, so not the bulk chemistry just moving from one place to another. And one way to do that is to move solids and gas at different rates so that you actually get your materials mixing around. And again, if that's coupled with non-equilibrium chemistry, then things don't reset. They actually retain the history of that motion of the relative amounts of material. So why might we actually have differential movement of solids versus gas? Well, it turns out that in a protoplanetary disk, small solids will migrate towards regions of higher gas pressure. The reason is that the gas itself experiences pressure support, which causes it to orbit at either sub or super Keplerian rates. And the particles, therefore, that are in the gas experience either a headwind or a tailwind. If you do the math, it turns out that the net result is always movement up the pressure gradient. So if you have a pressure bump, everything moves into that bump. So there's just a little cartoon of that process. And so if you have a smooth disk, and here's my horrible schematic of a protoplanetary disk, cut edge on. If you have a smooth disk, the inner disk has higher pressure, and so moving up the pressure gradient means moving radially inwards. But it could be more complex than that, and that is something we would predict if planets are forming. So if you stick a planet in that disk, you actually create pressure bumps sort of surrounding the planet, which become traps for your solid grains. And this is some of the many, many people who have been looking into this kind of scenario. And so ultimately then, our inner disk chemistry can depend on this movement, and the movement depends on the presence or absence of planets. And so it's actually kind of almost circular, where we have the planet formation process itself affecting the chemistry, which is affecting the planet formation. And so this has been sort of theoretical so far, but all the beautiful images that have been taken from ALMA, here's Sean Andrews' work on the left, this is from Feng Long on the right, are showing that many, maybe even the majority of protoplanetary disks do have structures in them. And we think that essentially what we're seeing here when we see something bright is that that is a pressure bump where the small grains are collecting, and that's why it looks bright to us. So if these structures are nearly ubiquitous, then this process is something we absolutely have to consider to understand planet formation. And so there's also been a little bit of a thought that maybe there's even a kind of fork in the planet formation road. So this is, I mean, I would say this is still very speculative, but there's some thought that maybe there actually are two distinct paths that a planet-forming environment can take. Maybe some systems do kind of stay smoother, and some develop the planets. And so if we think about the chemistry and what's happening in these two scenarios, the smooth disk is going to allow the solids to move in. And what actually happens is, let's say your solids are very water-rich because they're forming beyond the snow line. They'll bring oxygen in, and then your inner disk, which is where your terrestrial planets like Earth are forming, become oxygen-rich, water-rich, oxygen-rich. While you may have other systems where you form a giant planet and you trap your solids in a pressure trap, and then they don't move in, and your inner disk becomes sort of water poor or oxygen poor. So, we'll be revisiting this later in the talk, but it's interesting to imagine that there might be these two different paths, and you can also ask yourself, what path did the solar system take? All right, so I'd like to tell you a little bit about MIRI-MRS, which is the instrument that I've been using on JWST, and how it's helping us to understand the planet formation chemistry. So the idea here is that I just told you that things are super complex, so we do want to have some constraints on what's really happening. We don't want to just say it's too complex for us to understand. So we're trying to ground ourselves in observations. And the observations that I perform are in the infrared region, which is probing really sort of the few AU region of the disk. So this is within the snow line, so it's affected by whatever materials have come in from the outer disk, but it's really just the few AU region. So it's relevant to terrestrial planet formation, and it's also complementary primarily to millimeter wave observations, definitely complementary to millimeter wave chemistry, which is really probing more of the outer disk. It's sort of like right at the boundary of what can be done with continuum observations in the millimeter wave. So just to kind of give you a caveat here, an important thing to realize is that because the disks are very optically thick, we are probing the disk atmosphere. So we're not sensitive to the midplane where a lot of the planet formation is happening. That said, we do have this idea, and so this is a little disk schematic. I've been telling you about some of these things, your snow line, your movement of materials. But we can also sometimes think of a disk as having three very simple layers. We have the middle layer where a lot of things are frozen out. We have an upper layer where things are very, very affected by the radiation field. And then we have an intermediate layer where things are molecule rich. So the idea going behind all our observations is that, yes, we're probing the disk atmosphere. We think we're able to probe into this yellow region. And if things are well mixed, then maybe we do have a handle on what's happening further into the disk, even if we're limited to seeing the disk atmosphere. So that's our supposition. Of course, we support it also with models, but that's our kind of assumption here. It turns out that emission from molecular lines, which I'll be telling you about, it does require kind of special conditions. If you have just a well-mixed protoplanetary disk, you're not going to see emission from molecules. So it requires some combination of dust settling and a vertical temperature gradient. So let's say 10 or 15 years ago, it wasn't entirely clear that we were going to be able to study molecular chemistry in the few AU region, and that luckily turned out that we were able to do that. So yeah, so this is what I'll be talking about the rest of this talk, is sort of this molecule-rich region where we're probing the upper atmosphere, but we hope that we're sensitive to this whole molecule-rich region. Okay, so we want to get observations. What do we need? We need a really amazing infrared spectrograph. Here is, sorry, this doesn't look so great in this lighting, but this is a pre-launch spectrum prediction for the MIRI medium resolution spectrograph. You can see some of the molecules we might expect to see, HCN, CO2. Everything that's not labeled here is actually due to water vapor, which I'll be telling you about a lot today as well. So we need an instrument that can detect these signatures. And this is the schematic of MIRI MRS from the JWST webpage, just to give you like a little overview of it. So it has 4 channels. You can see there the channels on the left, they have these bands, and each band produces a band that you can see in the middle panel here. So it is an integral field unit. So it gets both spatial information and spectral information. And then you can, so this is what actually ends up on your detectors in the middle there. And then if you reconstruct what's on the detectors, you get your 3D image cubes on the right. And it observes from 5 to 28 microns, which is the region where we expect to see a lot of molecules. And I don't know if this is too obvious to say, but I'm going to say it anyway. Because many astronomers are not trying to observe things like water. And water is just in our atmosphere. So we're not just fighting against transmission in a general sense. We're fighting against transmission or absorption in our Earth's atmosphere of the exact molecules that we want to study in the planet-forming regions. So water being a key one, but also things like CO2, for example. So this just shows the mess of the transmission through Earth's atmosphere, which here is, a lot of this is due to water vapor if you try to observe from the ground. So having a space telescope is really crucial. Again, something maybe is obvious for this audience, but I just want to say it anyway, that sometimes JWST is thought of as a kind of follow-up to Hubble, but really for all of us, it's a follow-up to Spitzer, and Spitzer was really, really tiny. So JWST just offers this incredible increase in sensitivity due to the mirror size. So that's maybe the obvious stuff. What might be a little bit less obvious if you don't do this kind of spectroscopy, our emission lines are spectrally unresolved, essentially. And so that means that the strength of the emission lines are directly correlated with the spectral resolving power. So even if you had no increase in the mirror size, you would detect fainter lines with MIRI MRS as compared to our previous generation spectrograph, which was Spitzer IRS. So we just get boosted line to continuum ratios. And here's some actual data now. It's no longer simulated data. The black curve is from Spitzer IRS, and the gray curve just shows that shooting up of the line to continuum ratio when you increase your spectral resolution. And for our work, we're looking at these very complex molecules. I'll be showing you more of this later. This is a Spitzer IRS spectrum. But what it's meant to show is just how complex even a little, what seems like a single bump in a spectrum is. So I don't know, you can kind of pick one feature. So for example, this one. And these are the quantum numbers for that transition. And so the numbers, are just correlated with the energy levels. So you can see that there's just a wide range of energy levels contributing to a single, what appears to be a single line in a spectrum. So the spectral resolution also helps us disentangle all of those details a little better. So what can we do now that we have this higher sensitivity? Well, one thing that's really important is to expand our view of the parameter space. So this is a little cartoon from Heis Mulders just showing he had done some simulations of planet formation as a function of stellar metallicity and stellar mass, showing that you might get different types of planets in different regimes. And in a cartoon sense, what we observed with our previous generation of infrared spectrograph was sort of this. So we were able to see sort of solar mass and a little bit higher mass, but that was kind of it. We're only really looking at solar metallicities. So we would like to expand this view, if possible, with JWST. And if you didn't have the liberal arts teaching load and you could make a new plot, you might also make a plot like thinking about radiation field strength and system age. That's another two parameters that can be explored. So radiation field strength, meaning, are we looking at low mass clusters or high mass clusters, and system age. So far, we've kind of looked at few million-year-old clusters, and we haven't gone to younger or older. And the reasons for that essentially just have to do with things being faint. So if you want something with higher radiation field, you need to go further away. System age is kind of interesting because as the systems get older, the disks disperse, and so they just get fainter because of that. And as you go to younger systems, they just have a lot of extinction, so they get hard to see as well. So we're opening up this parameter space with our sensitivity. Now, JWST does have improved spatial resolution compared to Spitzer. And so you can ask, does it provide spatial information? And so I'm showing you this cartoon just to give you a sense of, here's our protoplanetary disk, but it's forming it's incorporated into this broader environment, which includes accretion from the disk onto the star, and also winds and jets. And so it turns out we do have some spatial information from JWST, but it's of this process and not of the disk chemistry. So we're not able to resolve the few AU region, but we are able to resolve this broader structure. So I'm going to just show you some cool images. I won't have time to really talk about these, but just to give you a sense that there is some spatial information there that is not really related necessarily to the few AU chemistry. So on the left there, that's results from Ilaria Pascucci. This is actually using the NIRSPEC instrument rather than MIRI, but what you see is actually different tracers seeing different parts. This is an edge-on protoplanetary disk, so it's dark here because of the dust extinction. The star would be in the middle there. And then these different tracers, so here's continuum, so it's actually the reflection of the light on the disk surface. And then you get a jet, a highly collimated jet, and a wider angle wind. So these beautiful images are coming out from JWST. This is a totally funky one. So we actually get, with MIRI MRS, it's an IFU, so we get images for free. We don't always know what to make of them. So this is an example of that. This is a protoplanetary disk that is more face-on rather than edge-on. And if you look at H2, it has like a ring-like structure, and it's actually asymmetric. So if you have any ideas for what's going on, let me know. All right, so I want to tell you about my team, JDISCS, and then I'll highlight some recent results and tell you kind of where we're heading. So what is JDISCS? So JDISCS is the JWST Disk Infrared Spectral Chemistry Survey collaboration. And just a fun fact for here is that this name was suggested by the SAO-RU student Phoebe Harritz. I don't know if any of you met her when she was here for the summer. Oh, so cool. So she came up with this great name and acronym for us, so thank you, Phoebe. So we're a little bit unusual. We're not really a team that is doing just a giant legacy survey, but we're kind of like a collection of JWST guest observer programs. We just chat with each other to try to learn from each other. So we have the PIs listed here of all these different geo programs. We also have many amazing students and postdocs who, as you all know, really lead the work. And so I'll be telling you about some of their work today. Sorry about that. So another thing that kind of collects our team together is a specific calibration process. So turns out MIRI-MRS has an issue called fringing, and not an instrument scientist myself, but my understanding is that it's standing waves between the actual layers of the instrument. And you can see it. This is in pre-launch data. It's a little hard to see. Maybe in this one you can see it most clearly. So it's kind of a wiggle pattern. And if you just plot the brightness versus wavelength, you get something like this. And I'll be showing you more spectra throughout this talk. It's especially problematic when you're looking at molecules, because molecules are producing these pseudo-periodic signals. So it's really important to get rid of that. So our process for dealing with this was really developed by Klaus Pontoppidan, but it was informed by a lot of work that many of us had done with Spitzer IRS. And it involves taking an asteroid and using it as a spectral response function standard. So what you do is you observe an asteroid, which you expect to be flat, and you actually first you have to kind of fit it with a black body. There's actually some interesting details here. I won't get into them, but it's actually not always a perfect black body for various instrumental and potentially scientific reasons. But you sort of divide that out so that you get something that you think is flat. And then all the wiggles that remain you assume are from the instrument. And then you divide out each spectrum by that response function. And so this, in theory, gets rid of all of your wiggles that are due just to the fringing. OK, so then we get our beautiful spectra. This is a selection of spectra from my Cycle 1 program. And I'll just kind of walk you through how to read some of them. So we see just a range of types of spectra. If you look at more massive stars, first of all, the reason all these spectra are not at 0 is because the protoplanetary disk consists of both dust grains and gas. So the dust grains are producing blackbody emission. And so that's why there's any kind of emission above 0 in general. And most of the spectra will show also solid state features here at the 10 micron, the SiO bond emission wavelength. The more massive stars, Herbig AE, BE stars, tend to show fewer molecules and more atomic features, and they sometimes show PAHs. And then as you get to the low mass stars, you start to see these incredible emission spectra from molecules. So some of them are highlighted here. If you go to the shortest wavelengths, you actually can see a little bit of the rho vibrational spectrum of CO. You can see HCN, acetylene, so some carbon-bearing molecules, and then essentially everything that's unlabeled is water vapor. All right, so I'd like to kind of highlight a few ongoing stories that are developing in our team. And I wanted to say up front, you're going to see like everything in this talk is from 2023, 2024. It's just amazing. And so I don't know all the stories yet. I don't know all the answers yet. I'm just going to kind of walk you through where we stand with some of these questions. So I want to first tell you about something that I've been working most closely on. So I'm working on this paper as we speak. And it relates to oxygen isotopes. And if you, I don't know how much experience you all have with thinking about cosmochemistry, but if you ask a cosmochemist what they're interested in the solar system, it's often isotopes and not sort of this very basic chemistry that we're talking about in protoplanetary disks. So there's kind of a holy grail, I guess, for chemistry of extrasolar systems. You know, could we actually measure isotopes and compare those and then relate that back to the solar system? So I'm going to tell you a little bit about the oxygen story in the solar system. The story basically goes that there's selective photodissociation of carbon monoxide isotopes or isotopologues. And the reason is that the 12CO becomes optically thick very quickly, so it doesn't dissociate beyond a certain level. But other CO isotopologues don't become optically thick, and so they dissociate. So you take your heavy isotopes of CO, you break them apart, and now you have these sort of free oxygens running around, and they can combine to make other molecules, and those molecules become heavy. So obviously one you would think of is if you have a lot of H2 around, you're going to form water, and that water becomes heavy. And so the consequence in the solar system is super interesting. It turns out that the isotopic ratios of oxygen become tracers of the origin signature of different bodies. So I'm not going to get into the exact details here, but just to say, like, this is a measure of the relative amount of 17 oxygen and the relative amount of 18 oxygen. And every body in the solar system kind of has its own space in this plot. It's a little complicated because the reason there's lines here is because things can also move along a diagonal in this plot because of just fractionation processes. So for example, like melting will tend to move the oxygen around, and so it can move it along that line. So we might ask, can we do the same thing for oxygen isotopes in protoplanetary disks? And some of this work, considering this, came from Jenny Callahan. So I'm going to show you what she did here. This is a model. So here we're looking at a crosscut through a protoplanetary disk. This is the height in the disk, and this is the radius. And what she found was that if you allowed this photodissociation process to happen in a disk, then you do actually get this enhanced region, or a region where the water is enhanced in H2-18O. That's what this white region is. And then she further asked, well, suppose you were to observe it with JWST, would you even be probing that region? And so that's what these lines are here. And you can see there's some overlap. So it is thought that we might be able to observe some enhancement in oxygen isotopes due to this process, which we know happened, or we think happened in the solar system with JWST. So that's what I've been looking into with this very, very interesting target. This is MY Loop. It is an essentially very high inclination protoplanetary disk. It has an inclination in the 70 to 80 degree range. So here's actually an ALMA image from Sean Andrews, that little yellow thing there. It's also, because again, we're observing with an IFU, so it's a little hard to see here, but maybe you can kind of see this web-like pattern coming out of it. That's actually, we think, an outflow for this sort of edge-on disk. So that's like what we're looking at. That's the context here. But if you look at the MIRI MRS spectrum, it's absolutely amazing. So this is the CO2 emission feature. But we also have, let's see if I can get these, 13 CO2. We have C18O16O. And then we maybe also have C17O16O. So we're actually seeing all of these isotopologues of water. Sorry, what? CO2. So we're seeing all these CO2 isotopologues. And we can start to ask, yes, it's not water. But for this CO2, can we measure the amounts of these isotopologues and see if it's isotopically heavy? And if so, maybe it was influenced by the presence of these heavy oxygen atoms floating around. So that's the holy grail. And now I'm going to tell you why this is really hard to do. So this is me airing my dirty laundry, so bear with me. But it turns out it's just really, really hard to model these spectra if you get into the details. So this is what I've been doing over the past couple months. These are 3 different models. They actually have radically different column densities. So we're talking 3 orders of magnitude difference in column density. What's troubling is that the differences in the spectra, they're subtle, but you can tell them apart. But the problem is there's actually no preferred model. So in other words, like if you look at this feature, it prefers the higher column density model, and you look at that feature, it prefers the low column density model. So it's really tricky, and it's telling us that actually our simple models are not even enough, really, to match the fidelity, the incredible detail of our observations yet. And just to give you a little more insight into this, this is some detailed information about what we're really looking at in those spectra. So this is the upper level energy of various lines in those regions that I just showed you. And what you see, and these are the quantum numbers. So what you see is, so some of them are kind of somewhat simple. But what we see here is all of these different upper level energies, and they're arising from, these are the quantum numbers, so as the numbers go up, we're seeing higher and higher vibrational states. And so it seems likely that the reason our models are not working super well is that there's non-LTE excitation, especially of these vibrationally excited states. So it's very difficult work to do, is my point. So I'm trying still to work with what we were able to do, and what I'm finding is, so this is a plot, again, where similar to a plot I showed you earlier, where it's a way of looking at the enrichment in 17 oxygen and the enrichment in 18 oxygen. And so if you have positive numbers, so if you're in this quadrant, that means you have an enhancement in 17 oxygen or 18 oxygen. And it looks like it's very confusing. It's maybe enriched in 18 oxygen. These are our measurements with 2 different methods, which I didn't have time to go into. So maybe they're enhanced. They don't seem to be enhanced in 17 oxygen, so that doesn't really make sense with any scenario. And so I'm not really sure yet. It seems difficult to do, but it's so close and so promising. And so I just wanted to kind of show you the details of this to give you a sense of what might be possible and also how difficult it is. But let me tell you some simpler stories now. At least this one, I think, is the most straightforward story we have so far. And this has to do with water. So I've talked already about the fact that we have pebbles that can move from the outer disk to the inner disk due to the pressure gradient. And it turns out, so all of our spectra are complex, but water is interesting because it's actually so complex that it becomes information rich, and we're able to kind of work with that. So I just wanted to show you something silly. So I foolishly decided to search, Google image search for asymmetric top. And so you get a lot of asymmetric shirts. But I love this because I feel like she's like water. She's like this diva molecule who like has this weird shape. And so that means that you get this really wide variety of emission lines. And with all of those emission lines, you can start to tease out some details. And so just to give you a little sense, this is an amazing paper that Andrea Bonsati put together. This, just to show you some of what we can do. Like, so here we have the solid line and the dashed lines are 2 different modeling techniques that our team was using and another team was using. And we're actually able to distinguish between them. So we're actually able to say, hey, you really need to follow this approach rather than this other approach. There's also, if you look at the spectra, some of the lines don't seem to fit the data of the simple models, and those are always lines that are from vibrationally excited states. And so you can actually say, hey, we can see the effects of non-LTE excitation, and we can actually sort of correct for those. So water is challenging, but also gives us a lot of information. And just a reminder from the story before, if we have really these 2 types of disks, if we have drift-dominated disks which are moving their pebbles in, they should have inner disks that are water-rich. And if we have disks that are trapping their solids, those should have inner disks that are water-poor. So can we see that in our data? And this was some awesome work by Andrea Bonsati showing he had this great idea to look at the drift-dominated disks, so they appear small in millimeter wave images because the pebbles have moved inwards, and compare those with the bigger disks that have trapped their pebbles. And what he noticed is that if you actually take a spectrum of a compact disk, that's the purple, and you subtract the spectrum of one of these structured disks, you get a residual. And that residual is consistent with cold water vapor. And so there's actually evidence, it seems, of this actual process of moving the pebbles inwards and having them release water vapor in the inner disks. So it's just really, really cool to see this dynamic process reflected in these static spectroscopic observations. That's just a couple disks that Andrea looked at, but Carlos Romero Mirza here at Harvard has been looking at this in more detail. So, and doing it kind of in more sophisticated way than just taking the difference of those spectra. So he's been actually modeling water column density and temperature as a function of radius. So these are column density profiles and temperature profiles. And then using that to ask what is the cold water vapor mass, and does that correlate with the disk shape or the disk size? And so here, the blue points here are the excess cold water vapor. And you can see that there is a nice anti-correlation with the size. So in other words, the small disks, which are the drift-dominated ones, do tend to have more water vapor in their inner disks. So this is a very cool story that seems, I mean, it almost seems surprising to me how well it's holding together, but it's been really, really cool to see it develop. All right, and then I'll tell you about the stellar mass story. This one is much more complex, just currently being developed. So coming back to a plot from earlier, JWST, one thing we hope is that it'll expand our view of planet formation chemistry to different parts of parameter space, and one part is to lower stellar masses. And you know, I'm motivated in general by just wanting to learn about stuff. But a lot of people really want to study low stellar masses because of the potential to look for habitability. So the lower mass stars are good candidates for exoplanet study for various reasons. They are, you know, the stars are fainter, so it makes it a little bit easier to do direct imaging, makes it a little easier to do some of your other characterization techniques. And there's a lot more of them. So for many reasons, exoplanet folks are really interested in low mass stars. And so it's really important that we understand those. So this was a really exciting result, not from the JDISCS team, but from a different team called MINDS. And what you're seeing here, and I have to admit, these are, I don't know, I don't think these are the most beautiful plots I've ever seen, but this is really bizarre, not at all what our spectra look like. You can see these giant bumps here. These giant bumps are not generally seen in our spectra. And those giant bumps are just loads and loads of hydrocarbons emitting. And so this is a low mass star, and it has this extremely rich carbon chemistry. So this, you know, made us question, are M-star disks, are the latest type stars going to have this carbon-rich chemistry? And if so, why? And I would say, this is me paraphrasing my interpretation of their paper, they really were not sure. And they said, you know, maybe it has to do with pebble drift. Maybe the pebble drift, I'll explain a little more about that in a minute, but maybe the pebbles are delivering carbon to the inner disk. Maybe it has something to do with the different radiation field of the younger stars. Or maybe it has to do with carbon grain sublimation, which I'll tell you about as well. So lots of possibilities, but this is only one disk. So our team also had an observation of a star with almost the same spectral type. This one does have some hydrocarbons, but nothing like that other spectrum. So it actually just looks kind of typical for our disks in our whole sample. So it looks like, you know, a sun-like disk, let's say, even though it's a later spectral type. So here is the observed spectrum. Here's a model. This is work led by C.Y. Hsieh, a grad student at University of Arizona. And so yeah, it has some hydrocarbons, but it's pretty typical looking. So why might that be? So these authors suggested that maybe carbon is transported by pebbles, and low mass stars sometimes have faster transport, but sometimes don't. So let me walk you through this. So what we think happens in the pebble transport is, first of all, you start by bringing in your water. And so you actually go down in time. You drop your C to O ratio because your O is going up. But then what we think happens is you might run out of the water. You've kind of brought in most of your water, and then you start to actually advect carbon-rich gas. And so your C to O then rises again. So this may happen for all disks, but it's expected because of the physics of the radial drift it's expected to happen faster for later type stars. So that's why you have different curves for different type stars. However, that's ignoring the whole process of the planet formation causing pebble traps. So if you instead have a structured disk, maybe your whole process is slowed down. So there might be sort of these many axes to consider, not just what your spectral type is, but also whether you have this structured disk or a small disk, a drift-dominated disk. But that's only 2 disks, so we have a third one now. This is actually a sun-like star that happens to be carbon-rich. So again, it still doesn't look as carbon-rich as that one weird disk from the MINES team, but it does have strong C2H2. It also has some other carbon-bearing molecules that we're not seeing in too many other targets. So this is work from Majo Colmenares. She's a grad student at University of Michigan, and she actually modeled this with a thermochemical model to try to understand what might be happening in this disk. So her suggestion is actually that we might be seeing sublimation of carbon grains, and that the amount of the carbon that you see that was sublimated is accretion dependent. So suppose you have a low accretion source, then your carbon grains, they sublimate and they release carbon into the gas phase, enhancing your C to O in the observable carbon-bearing species. But if you have a high accretion, that carbon just kind of gets sucked away onto the star and it's not available to see. So this is still, I think it's a complex story, but Majo put together this plot showing accretion rate and stellar mass and trying to understand these 3 targets that I've been telling you about in this 2-parameter space. So maybe this object here, it has a lot of carbon because of its low accretion rate, so it's in sort of this state. And then maybe these 2 objects that both have low stellar masses, they're both late type, but seem to have different amounts of carbon, maybe that's because they sit on a different part of this y-axis. So I think it's clear this story is pretty complicated. I don't think we know yet what the real stellar mass effects are, but it's a developing story, and it's really interesting to me. So let me tell you a little bit about where we're headed next, relating back to all the things I've been telling you about. So for the oxygen isotopes, we want to look for other isotopologues. One important one is H218O, and I will say we have found it, so I'm very excited about that, work in progress. And then we also need to work on our models, and do not ask me questions about this. This is a figure from Jeff Blake, just showing the paths of non-LTE excitation of water. So that's one of the things that we have some of our modeling experts working on currently. Another thing that we're looking at is the time axis for pebble drift. So these are models from Adrian Hogue showing expected water vapor mass versus time. And what you see is kind of an increase and then a decrease. And we have been looking sort of at few million-year-old objects, so we're just sort of in this part of the graph. And so if we could look at younger objects, we might expect to see really like an enhancement in pebble flux. And if we look at later objects, we might see a decrease. So we're in progress studying objects of different ages to try to see if we can see this evolutionary process. And I still don't know what's happening with the stellar masses, but I can say that I think the answer probably lies in looking at larger samples. So this is work in progress from Nicole Arulanantham. She is a postdoc who just left Space Telescope. And these are just beautiful plots she's been putting together, looking at all of the molecules that we see in our samples and trying to understand the sample as a whole. So I don't think we have the answers yet, but I do think that that is the direction we need to go, to think about the bigger picture. So in conclusion, the canonical planet formation story, that's not the whole story. I think that MIRI MRS is providing us the ground truth to try to test some of our ideas about adding complexity to our story. Some results that we have had so far, detection of isotopologues, which is pretty cool because it relates back to solar system cosmochemistry. We have pretty clear evidence that pebble drift is moving water vapor to the inner disk and influencing inner disk chemistry. We have some sort of stellar mass-dependent picture of carbon chemistry, although exactly what's happening remains complicated. And we're continuing to explore larger samples going towards different ages, different stellar masses, et cetera. So thank you.
Thank you for a great talk. That was really wonderful. Does anyone have any questions for Colette? Yeah.
Thank you for a very interesting talk. Thank you. So I'm assuming you're using Hydron, right, as a spectroscopic input. Thank you for that. So I have two questions. One is, how many unidentified features do you see in this?
Not a lot. Yeah, occasionally we do identify things that are not in Hydron, for example, and we've used like exoplanet databases, exoplanet atmosphere databases for other molecules that are not like abundant in Earth's atmosphere, but it's not a lot.
That's good to know. And my other question was, if you go back to this CO2 modeling, non-LT CO2 modeling.
Like way back?
Sorry, yeah.
Where all the data came from Hydron, that's what you're asking about?
Well, okay, yeah, we don't, yeah, or maybe even one before. So, yeah. So are you using Hydron or high temp here?
So it's high tram, but I think doesn't that incorporate? Maybe we should check. But I thought this incorporated high temp into it, the modern version of high tram.
No. So the problem is that for higher temperatures you need so many energy levels that we just cannot give it to Earth's atmospheric people because it will break their codes. so we keep it separately. So if you go to temperatures above terrestrial temperatures, one has to use high temp, and that's probably part of the reason why non-LT doesn't work, because we just don't have those levels there. And if you use high temp, and in fact we just submit a paper with new high temp for CO2, so we can give us a new line. So that could work much better.
Yeah, let's definitely talk then.
Yeah.
Thanks.
Any other? Yes, I see a question over here.
Thanks, Colette. Great talk. Can you go back to the slide where you showed the H2 rings? Because I think this had passed me by that we'd actually resolved rings of H2. I mean, maybe you could comment on this more, how real you think these results are, and if so, the potential for using JWST to study total gas mass distributions in disks and what we can learn from that.
Yeah, so I think I missed part of your question, but like whether this is real, is that what you're asking?
Yeah, I mean, sorry, maybe I misinterpreted how you said it, but
so it is real.
Yeah.
So we, like I said, we get these data for free. So we are working on a paper to put together like a gallery of what all of these H2 images look like. And you can try to estimate the mass. I think we don't know the velocities, but if you assume a velocity, then you can start to ask yourself, what is the mass loss rate? So that's the kind of calculations we're trying to do. And then you can ask yourself, what is the outflow to accretion rate ratio and things like that. So that's what we've been doing. This is one of the only ones that we've published. It actually kind of is the weirdest one. A lot of the other ones do look more like, a little bit more like this. They're not all, we have a range of inclination, so they're not quite as clear as that. But we do tend to see kind of a bipolar outflow wind-like structure. This one, we don't really understand. This is also seen in ALMA CO. Feng Long has some data showing that. So this is a really strange object, but it doesn't seem to be the norm.
All right, any other questions? Oh, yes.
Hi, I just wanted to ask, these are young stars, they're very active, there's a lot of flares, CMEs. So what sort of effect does it have on the models that you have? I mean, is it ignorable or is it substantial?
Yeah, I mean, that's also something we're looking into is how variable is the chemistry. In general, the chemistry tends to be pretty stable, or at least whatever we're observing tends to be pretty stable. I mean, we do also have we have Spitzer IRS data and we have the JWST data, so we're able to compare things on kind of a 10-year time scale. Things in general are stable. There are some objects, EX Lupi is one of them, which is known to be variable in the chemistry, which is correlated with its flares and things like that. So yeah, we're aware, and it's actually, luckily, it seems pretty stable for a lot of targets.
Hi, so thank you. You use the word pebble a lot. What is the pebble exactly? You know, how big is it, or how much do you know?
Yeah. Okay. So, I'm going to try my best to be a theorist here, but I think a theorist would say that a pebble is something that is kind of at the maximum drift speed for radial drift speed, and that I believe is sort of radially dependent. So I think the pebble size is actually a function of where you are in the disk. That said, the ballpark is centimeter sized. So yeah, ballpark centimeter sized. Yeah.
Any other questions? If not, I kind of have one big picture question for you. So what would you say your takeaway was for planet formation from the Spitzer era, and how has that changed with new JWST data now, if at all? Or can we say anything about that now?
Yeah. Yeah, that's interesting. I mean, I almost feel like we weren't, I hate to say this, I don't know that we had a lot of revelations about planet formation chemistry from Spitzer. I think we almost were able to say, like, yes, we can do this. Like, it's a possibility. The lines are there. They're detectable. But we didn't have all of these amazing details and revelations that we're having now with JWST. So I don't know. I guess I can poo-poo my old work here and say, I think we're doing a lot better now.
Yeah, really exciting work on the horizon. And I'm excited for like the big survey data. Now we're going to be able to say bigger things about planet formation. Any other last minute questions or short questions? If not, let's thank Colette again. Thank you all for coming.